Stars. They light up the night, but not all shine the same. Some flicker faintly, barely noticeable. Others blaze so hot they could vaporize planets from light years away. Every star has a story, its intensity shaped by mass, temperature, and how fast it burns. Some live trillions of years, quietly enduring. Others flare bright, die young, and explode in supernovae, lighting up entire galaxies. This is the story of the stars, from the faintest flickers to the most explosive giants, and what they reveal about the power and fragility of the universe. Level 0. At the very bottom are the brown dwarfs, often called failed stars. They form like stars, but they never ignite nuclear fusion in their cores. Too small, too faint. Their glow is weak, almost imperceptible. Brown dwarfs occupy a gray area between planets and stars. They can have masses up to 80 times that of Jupiter, but that's still not enough to trigger true fusion. Instead, they produce minimal light and heat. In the dark expanse of the galaxy, they are invisible to the naked eye, but detectable with sensitive telescopes using infrared sensors. Despite their faintness, brown dwarfs are common. Estimates suggest there may be as many brown dwarfs as regular stars in our Milky Way. Their energy output is tiny, but they persist for billions of years, slowly cooling over time. They are the quiet guardians of the cosmos, silent, enduring, often overlooked, and yet they tell us something fundamental about stellar formation. Not all matter in the universe achieves brilliance. Potential doesn't always equal power. Level 1. Step up and you meet the red dwarfs. Small, cool, and faint. These stars are the most numerous in the galaxy, making up around 75% of all stars. Red dwarfs are slow burners. Their temperatures range between 2,500 to 3,500 Kelvin, and their luminosity can be as low as 0.01 times that of the Sun. Their small size gives them a huge advantage: longevity. Red dwarfs can survive for trillions of years, far longer than any star like our Sun. The longest-lived red dwarfs will outlast the current age of the universe several times over. Their slow energy release means they barely consume their hydrogen fuel. Because of their faintness, red dwarfs often escape our notice. Many of the closest stars to Earth, like Proxima Centauri, are red dwarfs. Proxima Centauri is only 4.24 light-years away, yet it glows faintly enough that it can't be seen without a telescope. Interestingly, this star has an exoplanet, Proxima b, in its habitable zone, showing that even small, quiet stars can host planets with potential for life. Red dwarfs teach us an important lesson. Size isn't everything. Their unassuming presence belies their significance. While they may not dazzle, their numbers and longevity shape the dynamics of galaxies. Level 2. Now we reach yellow dwarfs, including our Sun. These stars represent balance. Not the smallest, not the largest. Stable, reliable, life-giving. Their temperatures range from 5,300 to 6,000 Kelvin, and their luminosity is sufficient to warm planets within their habitable zones. Yellow dwarfs are main sequence stars. They burn hydrogen steadily in their cores through proton-proton fusion, maintaining equilibrium between outward pressure and gravitational collapse. The Sun, a classic G-type star, has been shining for 4.6 billion years and is expected to last another 5 billion years before evolving into a red giant. Life as we know it depends on stars like these. Planets orbiting yellow dwarfs experience stable radiation, predictable energy, and long-term consistency. Photosynthesis, climate regulation, and planetary chemistry all rely on this star type. Systems around yellow dwarfs are prime candidates in the search for exoplanets capable of supporting life. These stars aren't flashy, they aren't the supergiants with explosive endings. Yet their steady, enduring light is essential. They are the stars that make life possible, the cosmic constants in an otherwise volatile universe. Level 3. Then come the orange giants, stars that have reached the later stages of life. Once they exhaust the hydrogen in their cores, they begin to expand, cooling slightly on the surface but increasing in size and luminosity. Orange giants can range from 1.2 to 4 solar masses. Their temperatures hover around 4,500 to 5,500 Kelvin, cooler than the Sun, yet their sheer size allows them to shine far brighter. These stars are in transition. burning helium and heavier elements in shells around their cores. Their brightness can increase to hundreds of times that of their earlier main sequence phase. Stars like Aldebaran and Taurus are classic orange giants. Visible to the naked eye, they dominate their portions of the sky. Their expansion foreshadows their fate. Eventually, they may shed their outer layers to form planetary nebulae, leaving behind dense white dwarfs. Orange giants illustrate stellar evolution in action. They remind us that stars are dynamic. Life isn't static. Fuel runs out. Conditions change. Brightness increases as the star swells, often creating dramatic effects for nearby planets. For exoplanetary systems, this phase can be catastrophic. Planets once habitable may become uninhabitable as the star expands and radiates more heat. Orange giants are spectacular but fleeting. Their time in this phase is a blink in cosmic terms, lasting only tens or hundreds of millions of years. Yet in that time, they shape the universe around them, enriching space with heavier elements through stellar winds that later form new stars, planets, and potentially life itself. Level 4. The universe escalates. Red supergiants emerge, colossal stars, luminous and immense. Their surfaces glow a deep red-orange, hiding cores that burn heavier elements at unimaginable pressures. They are the giants of the cosmos, visible across light years. Red supergiants begin life as massive main sequence stars, often 10 to 50 solar masses. Over millions of years, they exhaust hydrogen in their cores. Gravity pushes inward, energy from fusion pushes outward, and the star swells to incomprehensible sizes. Some red supergiants could engulf Mercury, Venus, and even Earth if placed at the center of our solar system. Their luminosity is staggering. Some shine 100,000 times brighter than the Sun, even though their surface temperature is cooler, 3,000 to 4,000 Kelvin. The cooler surface gives them their characteristic red color, but their sheer size makes them dominant. Take Betelgeuse in Orion. Around 20 times the Sun's mass and hundreds of times larger, it is approaching the end of its life. Its core fuses heavier elements in concentric shells. Soon it will collapse, ending in a supernova. Supernovae from red supergiants distribute carbon, oxygen, iron, and other heavy elements into space. The raw materials for planets and life. Level 5. Enter the blue supergiants, the heavyweights. They are massive, incredibly hot, and volatile. Surface temperatures range from 10,000 to 50,000 Kelvin, far hotter than red supergiants. Their color is blue-white, dazzling even to telescopes, and their luminosity can be hundreds of thousands of times that of the Sun. Blue supergiants start as stars with 20 to 50 solar masses. They consume hydrogen in their cores at an extreme rate, living only a few million years. They burn intensely, shining hundreds of thousands of times brighter than our Sun, but their lifespan is short because of their fuel consumption. Rigel in Orion exemplifies this level. Around 21 solar masses, it emits energy 120,000 times that of the Sun. Its brilliant light dominates the constellation. Blue supergiants are unstable. Stellar winds push mass into space at thousands of kilometers per second. These outflows can strip outer layers and change the star's evolution, leaving behind dense cores. Blue supergiants are precursors to supernovae, sometimes collapsing into neutron stars or black holes. They produce heavy elements and radiation that shape future star systems. They are both creators and destroyers, fleeting in presence, yet monumental in effect. Level 6. Beyond blue supergiants lie the hypergiants, rare, colossal, and extreme. Masses can exceed 100 solar masses, and luminosities reach millions of times that of the Sun. Surface temperatures often surpass 50,000 Kelvin, radiating enormous energy into their surroundings. Hypergiants are naturally unstable. Their mass and gravity create immense core pressures, while fusion pushes outward, generating pulsations and massive stellar winds. These stars can lose several solar masses in outflows during their lifetimes. VY Canis Majoris, a red hypergiant, has a radius over 1,400 times that of the Sun, capable of swallowing Mercury, Venus, and Earth if placed at our solar center. Blue hypergiants are hotter and more luminous, rarer still, living only a few million years. Hypergiants die dramatically. Their explosive supernovae or collapse into black holes seed the galaxy with heavy elements, shaping the next generation of stars and planets. They show us extremes, mass, energy, and cosmic influence. Level 7. Wolf-Rayet stars emerge as the final stage of massive stars. These stars have lost most of their outer hydrogen layers, exposing hot helium or heavier elements. Temperatures exceed 50,000 Kelvin, sometimes reaching 200,000 Kelvin, and their luminosity is extraordinary. Wolf-Rayet stars are short-lived. They burn rapidly, exist for only a few 100,000 to a few million years, and eject enormous mass via stellar winds. They are highly unstable and often the precursors to type Ib and Ic supernovae. WR104 in Sagittarius is an example. It spins rapidly and emits energy intensely. Some of these stars are part of binary systems, creating gamma-ray bursts when they explode. Wolf-Rayet stars illustrate the fragility of massive stars. Their energy and mass push them to the edge of stability. Level 8. Extreme luminosity stars, sometimes called luminous blue variables (LBVS), occupy this level. They are unstable, massive, and unpredictable. Their brightness can vary dramatically over years or decades, often ejecting vast amounts of mass. LBVS, like Eta Carinae, shine millions of times brighter than the Sun. They are rare, but awe-inspiring. Eta Carinae underwent the Great Eruption in the 19th century, temporarily becoming the second brightest star in the sky. LBVs are cosmic showpieces, demonstrating the violent extremes of stellar physics. Level 9. Some stars reach pair instability supernova thresholds, usually in the range of 150 to 250 solar masses. At these extreme masses, the cores become so hot and energetic that gamma-ray photons are converted into electron-positron pairs. This process suddenly reduces the internal pressure supporting the star against gravity, causing the core to partially collapse. The collapse ignites runaway thermonuclear reactions that result in a catastrophic explosion, obliterating the star entirely and leaving no remnant behind. No neutron star, no black hole, nothing. These events are exceedingly rare, occurring only in the most massive stars, but they are incredibly influential in the evolution of galaxies. Pair instability supernovae produce enormous quantities of heavy elements, including oxygen, silicon, magnesium, and iron. These elements are blasted into the surrounding interstellar medium, seeding it with the raw materials for new stars, planets, and eventually life. The energy released in a single pair instability supernova can briefly rival the light of an entire galaxy, illuminating regions of space for weeks or months. Observing these explosions allows astronomers to study the physics of the most massive stars, the chemical evolution of galaxies, and the cosmic cycle of creation and destruction. In a universe filled with extremes, pair instability supernovae are a spectacular reminder that even the most violent endings can fuel new beginnings. Level 10. Finally, the most luminous stars ever recorded, extreme hyper-luminous stars like R136 are one. With over 200 solar masses, it shines more than 8 million times brighter than the Sun. Surface temperatures exceed 53,000 Kelvin, and its wind ejects mass at millions of tons per second. These stars live mere millions of years, burning so quickly that they reach instability almost immediately. They are cosmic giants, rare, powerful, and short-lived, often ending in supernovae or collapsing into black holes. They demonstrate the upper limits of stellar physics, pushing the laws of fusion, radiation, and gravity to extremes. From the faintest flickers to the blazing giants, stars are the heartbeat of the universe. They create, they destroy, and they shape everything around them. Every star tells a story, and the next time you look up, remember, the cosmos is alive, and so is its light.